Hey, we are recording this session and we will talk about autoencoders today. So this idea of autoencoders is something that is pretty much what it should mean. It is an encoder-decoder combination. But what does that really do? And that is something that, first of all, understand where does it actually get applied? In what context do people actually use this thing called autoencoders? And why is it so cutting edge in terms of its evolution as we see. So one of the things that this thing comes in handy is the idea of what is called dimensionality reduction. Like you may have noticed in our earlier examples, we did discuss this thing called principal component analysis, in which we had a 3D plot of some sorts, a three-dimensional plot. And I'm bad at 3D drawing, but this is the three axes we have. And we have data somewhere plotted. And in that segment, we might have data on a particular plane that may not be exactly aligned with X and Y. It may be a little bit shifted like this. Like, maybe a plane, an arbitrary plane of your imagination that you can think of, that is different from the standard XY plane. This is your XY plane. This is a little bit shifted plane. And if you have data set that sits on a given plane, maybe in this imaginary plane that I just tried to draw, and it is actually in 3-dimension because the plane itself is not exactly aligned horizontally with X and Y. It is a little bit tilted upwards from the Z direction and downwards in this negative Z direction. So it is shifted plane, think of it that way. And that makes it a 3D data set. But if you notice, if you happen to have data set is strictly limited to only that particular tilted plane, we can potentially reduce the dimensionality of that data set from 3 dimensions down to 2. And we did that in an example before. I think we called it principal component analysis. And by doing some math, what we were able to accomplish is this simple idea, is that we were able to basically take this plane and convert that into an imaginary X and imaginary Y axis. Not this X, not that Y, but imaginary X, imaginary Y. That goes along in somewhat like this direction. So like this plane's direction. So that becomes your imaginary X, imaginary Y. And then by doing it that way, by realigning our axes on those plane that align with this artificial plane, or rather I should say inclined plane, what we are able to essentially accomplish is we can now afford to kind of forget the Z axis, because we are now dealing with X prime, Y prime. And the reason we can forget is primarily because we have made sure that we are aligning our what I call dimensions, the X prime, Y prime direct dimensions to the inclined plane itself. If you want to convert this into a, if you recall PCA, maybe I can skip ahead, but if you don't recall, that's the way to think about principal component analysis, in which you're reducing 3-dimensional into 2. So we can work with a smaller number of dimensions, thereby finishing the computation faster. So that's one area, dimensionality reduction. The other area where it is becoming extremely useful, which is probably the dominant case these days, is the area where we have a lot of unstructured and also unlabeled data. Labeled data is something that we already know what it is, which is, if you have this picture of a number that looks like the number, let's call it the number 3. So this is how I draw 3. And to me, this looks like 3. To some people, it might look like 3 also. And so but to a computer, the computer might read it like, oh, that's a 3. That's your label that you assign to this image. And this is a numerical value. So for a large collection of images that we might have, we will have to have a person, a human being, has to come in and label every image. So I have 60,000 images. They become labeled by a human being, like, that was a number 2. I see. That's a human label. But getting these labeling done is kind of boring. It's actually boring if you think about, go to the beach and collect pictures of stones, like bunch of pictures. You find a bunch of stones on the beach and you just take pictures, all of them. You bring in like 70,000 pictures. Now ask people, can you look at each and every picture that you have taken, that you took on the beach, and find out if that stone is an agate or not? That classification has to be done by somebody. Some human has to go and classify. And that's how we can create a labeled data set. I should say labeled data set. Now this action of generating labels to a large number of images as an agate or not is a hard human problem. It is boring, it is expensive, it is cumbersome, it requires human beings to actually look at each and every picture and then come up with yes or no. No, and this is yes. And so that decision making has to be done to begin with, to collect a labeled data set. And once we have that, then we can, of course, assign this into an X array, and the Y values, the labeled data itself becomes Y, the images become your X matrix and the Y matrix. And then you can use some algorithm to train using this data set. And then that algorithm will learn to then decide whether a new picture that you feed is agate, yes or no. So that's a classification problem, that we have this data set that we collect from the field. Go to a beach, collect pictures, bring them, classify them manually. That's a manual step. And what this actually does is that this technique of autoencoders is the reason it is getting immensely popular. It is this idea, which is it can be used for unsupervised pre-training. Even if you don't have a lot of labeled data, you can still collect, out of the 70,000 images, let's say you label only 1,000. That is probably doable as a manual task, and you leave the 69,000 unlabeled, but you keep them because that's a useful way of, now that you have the pictures, you just store them. And we can potentially apply techniques in here in autoencoders to use the unlabeled data set as input, as specifically unsupervised pre-training segment. And I'll describe what that idea is and why it is relevant and where this thing comes into play to make it really, really interesting, because it does save money. Save money, save time, save effort. The effort and money and time saved is basically in human labeling. That is a hard one. Doing it on 70,000 images, anybody would get bored. Maybe ask them to do 1,000 images, they can possibly grudgingly agree and do it and manually label it. And so now you have some labeled data, and this is unlabeled data. And you have that data set, this 69. And so you have some labeled data, some unlabeled data. You basically want to optimize your time, your money, your effort, and minimize the work that people have to do, and see if you can automate some of it. Not to a great extent, but at least some of it. So not the whole thing. It will not magically detect whether a picture that you took of a stone is an agate or not. It doesn't have any idea about that. So here to first of all help the machine itself understand what agate is. That's where this thing comes into play. And then it'll use the underlying features. And that's where this third idea comes into play, is that it is able to detect features of the underlying imagery or underlying data input that you're trying to transmit and pass through an autoencoder. And we can, once we have the system trained to detect those feature sets, we can reuse them in other techniques, in other decluttering techniques that we have discussed, like convolutional neural networks, or long short-term memory, or all other things that we have been discussing up until now, or even your regular fully connected neural networks that we have seen in the past. So all these varieties, we can apply these techniques from autoencoders into our conventional ways of using neural networks to automate some of our tasks. That's the underlying idea. That's where this is coming in handy. First is dimensionality reduction. The second one is detect features, new features. And third one is basically pre-training, automated pre-training, unsupervised. Pre-training, unsupervised. This is the sexy part, unsupervised. That you don't have to do anything. You just give it to the machines, and they will attempt to generate a pre-trained data set. Think of it as it will help you optimize to some extent the work you have to do otherwise manually. That's where this thing comes into handy. Now, exactly how this autoencoder works, what exactly is going on under the hood, that's what I would like to now briefly describe. And that idea is why is it going thicker and thicker? Oh, this is good. This is good. Okay. So I will now describe the idea behind autoencoders. So it is actually kind of crazy, a very crazy idea. Think of it like this. So if you have a set of input, let's call this set of input data, and you feed it into a system, and you have neural network layers and layers and layers, and at some point you say that, you know what, that's enough depth for us to discuss. So we have 2 layers, 1, 2, and then we will create a layer that is kind of sort of a mirror image of what you saw here. Down, we'll create the same thing here. And so we will have another layer containing that kind of matches the size of this. The number 3 will match number 1. And this is the original input layer. And so you have the final output layer will match the input layer size. So the size of neurons you will have matches the input. The output also matches the input approximately. So that's the underlying idea. So what we are really doing is we are creating an identity function, y equals x. This is your y, this is your x. That's the identity function, y equals x. That's what we attempt to create in this system. But as you will notice, we are putting artificial constraints in here by either narrowing it down, like limiting it like this, by shrinking the number of neurons in the middle hidden layers, and still forcing the function that making sure that output resembles input. Output resembles approximately the input. That's the constraint we'll put on the top and force the machine to learn what are the really, really key things for the machine to actually produce the expected output, which matches the input, even though it is passing through a narrower, or I should say, there is a word for it. The word is, I think it should be there coming up. The word is, what's the word? Yeah, it will come. There's a keyword that they have defined. I think it is undercomplete or super complete, or one of those words. It will come. And I just need to remember that word. So I'll go and look for it. Undercomplete, I think. But yeah, so it will come when we get to it. So for right now, let us understand one another characteristic. Maybe this is a good example to think of. If you think of this, if I ask you, hey, can you remember these 2 set of numbers? Which one do you find it easier to remember from just a quick look? And you might say that the first one is a smaller set of numbers, so I'll probably find it easier to remember. And that's the first expectation people will have with this set of numbers. But if you actually look and try to detect patterns in the string of data that you are looking at, you will find that this is actually a sequence called the hailstone sequence, which essentially is this: even numbers are followed by their half, and odd numbers are followed by their triple plus 1. So even number followed by their half, and odd number are followed by triple plus 1. Even number followed by half. Odd, and this is even number followed by half. This is again even numbers followed by half, and a triple plus 1, like that. So it's very easy to remember once you know the pattern. If you have studied the data set and if you know the pattern, the only constraint that you need to remember are these rules. If it is an even number, then you half it. The next one is half of it. The next is half. That's one rule. You need to remember that one rule. The second rule is, if you find an odd number, you make it 3 times that number plus 1. That's second rule you need to remember. And then you need to also remember how long will you go and what is the beginning point. The beginning point is 50. You need to remember how long will you go like this, following these rules. And that's how you can reproduce the entire data set very, very succinctly, as opposed to this data set, which is basically you have to remember it as it is. And that becomes difficult, comparatively speaking, compared to remembering this. So what we are really looking at is the understanding of the concept, is that we are putting constraints and we are feeding this data, this one, so let's call this A and B. So we are feeding the data A into a system, and we are not putting any constraints as such. We are remembering the whole thing, and we produce the output. The output is A. So whatever you provide, the same thing is remembered and you produce the output. There is nothing going on here. It is an identity function, just passes through, no modifications as such. Whereas in the other case, you pass through this B as an input, and there is some calculation or some understanding of patterns within the data set that you are feeding into the system is happening. It will still produce the output, which is, of course, matches B, but in here, you don't have to actually remember all these numbers by rote, because what you are actually going to remember is the set of rules that we have found out, which are these. So the even, and then followed by next is half, and then odd number, then you followed by 3x plus 1. That's the set, the 2 rules. Then you have a beginning point, and how many count these are, 1, 2, 3, 4, whatever that number is. So you have to remember that there are 17 numbers. I'm just making that number up. So 17. So it's a random number. So this is the length. And so what you're really constraining yourself within the system, within the boundary of the system, is to not carry a record of each and every of these items, but only the patterns in the data. You can ignore everything else. You don't actually need to remember all these numbers, because you can absolutely reproduce this same exact thing. And so in your system, you're constraining the system and thereby forcing it to learn what the patterns are in the data. And thereby you're able to produce the data without actually making, or rather, without blindly copying like this. So you have to basically keep track of every single data point here. And these are artificially small sets of data. Imagine if the data set is really large, really, really long. Then it becomes really difficult to actually keep track of such data, and you have to produce the output. So it's an easier option to detect patterns in the incoming data. So you can actually produce the output that almost matches the incoming data. That's the concept behind autoencoders. Another example I think that we have is this case of a famous study by these guys. And that study is basically a chess player. So we have a chess player playing. I think some lighting flickering is happening apparently. So let me adjust the flicker. And the pattern in chess is something like this. So if you look at if you are an expert chess player, let's see, this is a chess board, and I have some king and whatever other pieces placed out in two different colors. So this is the black and this is the white, two colors laid out, and some placements are there on a board. This is chessboard, and if you ask me, I'm not an expert chess player, so I have to remember how is the balance or how is the actual positioning of the game between the black and the white on a given chessboard, and what can be the next strategy. I have to actually remember the physical position. Each and every item on the chessboard, I need to remember the things in order for me to reproduce the exact state of the board. But if you look at expert chess players who've been playing it like a profession, if they look at a board, they can very, very systematically re-articulate the same exact board in a fairly quick amount of time compared to the amount of time it will take me to remember each and every position, every single piece on the board. So what they're really doing under the hood in their brains, since they have played the game so much, that they're able to tell the patterns of motion or movement of the items on a chessboard, and they're able to detect those patterns, and thereby it is easier for them to just glance at a board and tell what is going on, and they can potentially think about these things in their mind as the underlying idea, where you don't actually need to remember the position of each and every item or other piece on the chessboard for an expert. And that's a similar idea here, because what they're really doing is looking at patterns on the data and are able to reproduce the same chessboard effortlessly, comparatively speaking. That's what the underlying logic that's going on here. Another idea is the same thing articulated here in a visual form, where the chess person has an input. He is thinking about what that actual pattern is. And if you ask me, it becomes hard for me to actually decipher. It's because I'm not a regular chess player. I occasionally play, but that's only occasionally. And what this person can do effortlessly is he can reproduce the output that matches the input, because he can, in his mind, the internal representation is not the actual X and Y location of, let's call this the X-axis, the Y-axis. And so this is not how they look at. So if you want me to remember the position of each and every item on the board, I will basically have to plot it on an XY graph and remember all the data points. And then that's my internal representation, which is more like this: Y equals X. But that's not what the idea is behind autoencoders. At the end, yes, that's what you will receive. Output equals input. But in the interim is where the magic happens, is that you are forcing the encoder to shrink compared to the input available, so that it is able to learn patterns in the data, and it produces the same output that you expect, which is input. But at the same time, this encoding and decoding is able to actually understand what the essence of the data underlying is. So there is some encoding that's happening here, and there is a decoding step happening. So it's going to reconstruct the whole board as it was, and it will attempt to replicate what the input was. And thereby we are able to get this encoding, decoding to happen. The same idea applied to, say, a music file. So you have a music file. It is a WAV file. So that's the raw format. And you encode it in MP3. And then this raw format may be a large file, let's say 100 MB file in raw format. You encode it to MP3, it becomes a 5 megabyte file. And you encode it to MP3 in some lossy fashion, which is how the nature of this MP3 is. So it is lossy by nature, the encoding of MP3. And so it will to a human ear, it will almost be equally good, but it is mathematically lossy. And that's the nature of this function of encode. So you get the output, which is small compared to the original raw file. And when you decode and play, a human ear cannot even tell. Most human ears. Some people can. I cannot. So human ear, when the machine decodes and plays the MP3 back, you hear the same music. that was originally to begin with. It is passing through an encoded decoded fashion and is able to reproduce the output, which was matching the input. So the output matches input again. That's the encoder decoder scenario in an MP3 file. If you look at a function which is lossless, so for example, if you take a look at not MP3 decoding, but something like what is called FLAC decoding. FLAC encoder, it's an open source encoder, free lossless audio codec. That's the name. So you pass the original music file, 100 MB, and this is by its nature lossless. So it is producing an output file of maybe 7 MB as opposed to 5. So it's also efficient, but not as efficient in the storage compared to MP3. So it's a trade-off. And then you, of course, when you decode, you get the exact, mathematically exact same raw file. This was raw. You decode and you get the exact same raw file byte to byte. And therefore, it is identical. Like, y equals x. This is y approximately equals x to a human ear. So that's the approximation. Sometimes kicks in. Sometimes it is absolutely accurate, lossless. This constriction or narrowing of the passage, which is the nature of encoding, is what we really are trying to go after. We want to get this out of the system. It helps us detect patterns in the data. And that's how we will be able to apply these concepts to an original data set in which we might have a large number of data points which are not labeled. And so we'll apply these encoder data points to that input and see if we can use them to construct the output that we expect as if it was fully labeled data. So we will be reusing some of the components from the underlying encoder layers within an autoencoder, extract information from here, and use it in our regular CNN, LSTM, fully connected networks, other types of networks. We can basically use the layers from the encoder sections of an autoencoder and let it run on the raw data as is without even human labeling, extract some important features that we want to then grab, understand them, and then use it here. Speeds up the whole game and actually avoids some human cost involved in manually dealing with the data. This is just only 70,000 pictures. Imagine if you're dealing with images of people at large, like Google Photos, for example. It is humanly impossible for anybody to do that. And so you have seen some what is called unsupervised learning of Google Photos with some little assistance that you provide, and it will identify, oh, that picture is Nilesh and that picture is not Nilesh or somebody else. And that detecting of what features comprise, or I should say that in English correctly, what features of Nilesh constitute the item known as Nilesh is something that needs to be detected. And if you ask a human being, how does Nilesh look like? They can tell. Maybe they cannot tell, but they can tell whether it is Nilesh or not by looking at it. Similarly, if you look at a picture of a puppy, well, puppies are always cute. But if you look at any picture, you can tell whether the picture is cute or not. And that requires human judgment. But if you ask people to decide what constitutes features of cuteness, they'll think that you are crazy. And, that's how people are when people are crazy. So what we're really getting after in autoencoders is we want to identify the features that we can mathematically represent and use in other neural networks so that we can expedite our work. That's the underlying concept behind this autoencoder business. Let's go forward with it. So yeah, the word I was looking for is undercomplete right there. And so similar to this undercomplete idea, there is the opposite idea also called overcomplete, which is, we'll get to that also. So this is the undercomplete encoder, which is the underlying idea is you're constricting or rather limiting your network and thereby forcing it to learn, or forcing it to learn the patterns in the data that we can reuse in other cases or just use it directly in a autoencoder itself. Okay, let's see what else we have here in the concept. I'm just checking if I miss anything here. I think not. Okay, so an example of principal component analysis. The idea is basically the same thing we saw before in an earlier example. This is the picture that you probably saw in I think in one of the first chapter number 4, I suspect. We have an original data set, which is on an inclined plane. This doesn't belong on the X or the Y or the Z axis it's just its own plane. It's a plane. And we want to basically see if we have some data set that we can drop projections, drop a perpendicular on this plane. So from every data point that we have, so for example, this data point, we are dropping a perpendicular like that. So if I may zoom, you will see it. You will see that these black lines are dropping perpendiculars on this imaginary plane. And then we get these black dots compared to the actual dots that we are blue in color. The drop perpendicular points are black in color. And they are close approximations of the blue points because they are almost on the plane, which is minimizing the distance. I should say this in a different fashion. Minimizing the error that happens between blue and black. The fact that we are going to use black, but the actual data point is blue, causes an error. And what we want to attempt to do is to find this plane that minimizes the error function. The error calculation will basically rely on the difference between blue and black. So if you notice, some of these points are directly on the plane. By the way, we have to actually derive where the plane should be. And that's the essence of principal component analysis. We don't know where the imaginary plane is going to be. And we want to find out that position of the plane in 3 dimension. Where does the plane lie? Or rather, which plane will minimize the error? The error will be calculated based on difference between position of blue and position of black. Black is a projection of blue. And you can do that for every single data point. All the blues are data points. Blacks are the corresponding drop perpendiculars on the imaginary plane that we want to find out. So there will be some plane which will be the optimal plane, which minimizes the error function. And while doing that, what we really accomplish is a plane in 2 dimensions, which is the imaginary function. So if you look at this plane that we're looking at, that's the same plane here. Same exact plane projected on 2D. And here what you see, blue dots are actually the black ones from there. So the black from here are blue here. And now we have the data set, put perpendiculars on a imaginary plane and flatten that plane into a 2-dimensional space. And this preserves the variance of the data. At the same time, we are dealing with 2 dimensions. So it helps speed up. So that's one area we can use autoencoders to reduce principal component analysis. Apply autoencoders to help us with PCA. So there are other ways to do PCA also. This is just the neural network ways of doing PCA. If you want to use it this way, that's a possibility. And when you are dealing with just deep learning and neural networks only, it is probably easier to just use this technique as opposed to the other scikit-learn technique. So that's the underlying idea here. You have an example that shows how will you go about calculating. And what we are really looking at here is a simple linear autoencoder, which is you provided a 3D input. It gives you codings. These codings are the output of an encoder. An encoder essentially is an interim layer. So you give it a 3-dimensional input data, and you force the output to be matching the input at the end product to match the input. And in the interim step, you will find that this encoder gives you codings, which are essentially 2-dimensional representations. So that's a hidden layer, 2-dimensional coding. And what we are really doing here is trying to reduce the output minus x. So this is your mean square error. The distance function that I mentioned before is the distance between your, where is the picture? Yeah, the distance between the position of blue and the black. That same distance, I want to minimize that, and that is what this calculation is going on right here. This one. And so we want to optimize and minimize the reconstruction loss, which is basically a mean squared distance between output and the original input. You run the optimizer, and actually we run when we run a session. So in TensorFlow, the things don't run when you actually lay them out. It runs when you actually execute in a session that is coming up in the next. So this is where the sessions is invoked. That's where the actual execution will happen with the initialization step, and you get your coding evaluation as an output. So that is something that we have seen before in this example. There are more examples where we can actually put this to use in a much better way. And so one of the ways to think about is that we can put multiple layers of these encoders if we need to. So they're called basically stacked encoders. So a stacked encoder is basically you have, say, multiple such layers on top of layers on top of layers. So it goes on. And of course, you can limit and be reasonable about how much deep can you go. But training these multi-layer or stacked autoencoders is to do it one of them one at a time. That's the way to train these things. When you have lots of them, you want to really train them in a very simple fashion, which is if you want to focus on one of them at a time. So if you're trying to identify and work with that layer, you will provide it input from here and expect the output to match. And so you deal with one layer at a time. That's the way to think about a multiple stacked autoencoders. And I'll give you more examples as we go along. So one of the cautions here is to not make autoencoders too powerful. What does that mean? It means, it is likely to run into a situation which is called overfitting. So you don't want to be doing that situation where, you have too many layers. It might actually do exactly what you want in the training time, but not be able to succeed in testing time. That's a possibility. So don't go overboard with this idea of stacked encoders, although you can. So nothing prevents people from doing what they want. So let's, another thing to remember here, in a stacked encoder, it is typically symmetrical, meaning the length of this and the length of this, number of units in that, they're kind of symmetrical in nature. So here, so you can see that we are going to potentially input our MNIST data set. It's 784, which is about 28 by 28 pixel image as an input. And we expect the same to be the output. So output matches input. Out matches input. That's what we expect. But we will use what we will have here in our layers as data that we can apply to other cases when we don't know what the images are. In fact, in another example coming up, you will also see that these kind of autoencoders can be used to actually write numbers. Like, you will see examples of the system generating new human written letters. For example, the way I write number 3 versus the way some other people write number 3, or some people write like this. Who knows? Maybe not. maybe they do. So, but the idea is that you can also train autoencoders to create data. That's another usage that you will see as an example coming up. So, by the way, in this example, what we are looking at is a symmetrical autoencoder that looks like a sandwich. Actually, this sandwich is not the right word. In fact, I don't like that word. Although it is like a sandwich, but sandwich doesn't mean that it is an hourglass shape. So a sandwich typically to me means it is a flat shape, or rather equal length or equal width shape. It can be an hourglass shape. So that's the way I would describe. But again, it's for us to understand what the point is, not the nomenclature. So the underlying idea here is that we have 784 units to account for our picture inputs. We will have a hidden layer with 300 units, and we'll deliberately constrain. And this is where we'll extract our codings from. So the encoding that is happening. And we will then at the final layer, the output layer, we'll reconstruct whatever this coding encoded. And we expect the output to match the input. Let's see how it actually works out in an example. So here is an example. In this example, I think it should be runnable. So let me go and open it up. By the way, the other time when I was running this thing, there was a bug that I think the bug was in my machine. So that I think I was able to fix it eventually. And so it runs. So there was even in 14, the other day it was not running. I think it is running now. The bug was in my setup. And that is one of the reasons why I don't like to run it, the machine sometimes. I have to maintain the machine. That's a problem. And so that's why I actually recommend using a cloud machine. And we'll do that. I think I already mentioned to you, Google Cloud is what I am inclining towards. I'll just get a machine created in that cloud and run these exercises there so that they maintain the machines and I don't have to maintain it. And so that's the idea behind is to outsource. That's just a simple way of saying that, I messed up in setting up my machine, which does happen occasionally. And so that's what happened the other day when our chapter number 14 exercises were not running at all, but they are running now. Having said, let's focus on 15 today. And so let's see if we can find this particular exercise in the autoencoders chapter. And it should be, there are other examples first, which I think I skipped. But let's go run through all of them, whatever we have. So let's begin with the first step, autoencoder step. I will also close out on the 14 chapter. I'll shut down that notebook so it doesn't cause trouble. I'll stay the 15 open, keep it open, and then begin running step number 1. And so we'll import a bunch of things. We also have this thing called save figure, which will save us a picture. So that's a function defined here, importing bunch of libraries, plotting capabilities, and a picture saving function. That's what I'm going to run right now. And so doing that. And then utility functions, we are creating some. So plotting image, plotting multiple image. So 2 more functions defined. And then we'll do the autoencoder exercise, which should be, I think we already discussed this briefly, but this is to build a 3D data set. So we are using randomizer or random NumPy random function to create a random data set. And this is the data creation step. So the data is going to be generated into 3 dimensions, 0, 1, and 2. And then we will normalize the data. So let's go first generate the data set and then normalize it. The normalization happens through standard scaler, which is going to do as a part of your scikit-learn library. So we are, use that scikit-learn here to the standard scaler to standardize the data set. Having seen this portions, let's go forward and build an autoencoder. Now this autoencoder is a very, very simple one. It has, the y equals x behavior. So basically unity function. So that basically produces the output that matches the input. That's the underlying concept. We'll use this to identify how we can reduce the dimensionality from 3 to 2. And now we will, now that we have generated some data, We'll now use that to build an autoencoder and run it through that. So running it now in here in this segment, what we are really doing is importing TensorFlow, reset the graph, setting inputs, setting our internal layers as our encoders. Our rule is our outputs matches input. That's the expectation that we have. We set a learning rate. We set a X as a placeholder variable. We define a hidden layer and output layer. So 3 layers. We are calculating our reconstruction loss as a root mean square function. So the squares of output minus X, the differences, and we want to reduce. And then we run Adam optimizer, just another optimizer, variety of optimizers we have seen early on, and pass in the learning rate. We have set it to 0.1. And then we get the minimizer to work on reconstruction loss. So we are trying to minimize this loss and initialize, and then actually run in the next step. So this is just initialization step. The actual invocation happens here, and we will now go run that. So clearing this, and now invoking our initialization step. Then we are specifying here that we are going to create 1,000 iterations and run a TensorFlow session. By the way, this red ink that you see is a deprecation warning. It is not an error. It is saying that something is deprecated. In the future, it will be treated as something else. So that's a deprecation warning, not an error. So don't have to worry about it as such until eventually we'll have that updated. But right now it is just a warning. Having seen that, we are going to run this iteration 1,000 times. And we'll then plot the figure. So the iteration is probably happening right now. Let's go check. Apparently it finished. How quickly? Huh. Let's do it one more time. So we'll import TensorFlow again and do the iteration one more time. And now it is running. You can see the runtime kernel running, and these things are running here. That should finish, and it looks like it finished. So when it finished, we should see our output. So now our next step should show us the plotted figure. So the figure shows up. What we see is the 2-dimensional data set reduced, which is what we expected to see. And this is, by the way, a randomly generated data set. That's why the picture doesn't match what pictures we have here. In our 2D example, this is a different random because it is random. Next idea is stacked autoencoders, which is what the exercise we were about to do, which is this picture on the right side. We are going to feed it the mnist data set and identify what this autoencoder will do for us, and how do we implement that in a TensorFlow scenario. So let's go see that. The first thing we notice, use mnist data set, so we import that. And then train all the layers at once, which means we have to have these 3 layers. A couple of things to observe here. There are some choices made here that we have to understand. The choices made are, there are 3 hidden layers, 1 output layer, and that means the picture will look like clear. The picture will look like this. So there is 3 hidden layers, so meaning 1, 2, and 3. Then 1 output layer, which is this out, H3, H2, H1, and then the input layer. We have 2 stacked autoencoders. We will use ELU activation, ELU. Hey or ha initialization and L2 regularization. Those techniques will be incorporating in this example. And let us begin with resetting the graph. And I will need to erase my ink so I can move my mouse. And there we go. So now we are initializing first in this segment. In this segment, we will be initializing. And then in the next segment, we'll be running TensorFlow. So that's the run step right here. So initialization step, let's see what we have in our hand. So reset the graph to begin TensorFlow creation. We have input layer defined as MNIST dataset pixel size 28 by 28, hidden layer 1, hidden layer 2, and then we are defining hidden layer 3 equals hidden layer 1. That is a match with this. See, this matches this. That's the idea of hourglass. And so essentially the auto encoders are these two. These three are hidden layers. And this is your output, input. That's clear. So also a constraint we are putting is that output matches the input. So whatever we have here should actually match what we feed in. That's the forcing function we are putting on our two layers here, these two. And they are our encoder layers. And this is our decoder segment. And that's our ultimate final reconstruction phase. So we are setting a learning rate. We are setting a regularization hyperparameter, L2 regularization, which is what we called out early on that we did. We are setting a placeholder. We are specifying the shape of the data set as the number of inputs, which is this 28 by 28. And then setting up ha initialization, which is another way to write that same thing is here. We are setting L2 regularization, calling this function here with a parameter that we are passing, which is this value here. And then creating a dense layer, calling out our ELU function, ha initializer, L2 regularizer, and then creating our layers, hidden 1, hidden 2, hidden 3, and output layer based on what we chose in these examples, hidden 1, hidden 2, hidden 3, and output. In the output layer, we have no activation function called out, meaning we want that to be exactly what we match the input to be. And then we construct our loss function. This loss function is going to be the output minus input, this input. And we take a square and then take a mean. So that's root mean square, RMS. There's no root here. So just mean square error. So just MSE, no root. Mean square error. That next idea we are doing is regularization losses. Then we are adding our regularization loss to the reconstruction loss. And this regularization loss is a factor that we are inserting as L2 regularization, which if you recall from the first time we discussed L2 and L1 regularization is basically forcing the loss function to be a little bit extra added on top of the mean square error. So this is MSE plus L2 regularization loss. Those two are added to calculate this loss function, and then we'll optimize on this loss function. And that's what we want to minimize on. So optimizer, minimize this loss function, which is a combination of mean square error and L2 regularization. And that we'll be able to initialize that and then create a saver function so we can save. It's not shown in the book, but doesn't matter. It's how you can save the state of the function that you run. So you run through a training step, you can actually save and resume operations for a subsequent run. So they save the parameters if you like, which you may want. And so that's the idea behind our initialization step. Now we will run the initialization step, which I haven't run yet. So I'll run the step number 10, and then I will invoke the actual TensorFlow session. Before that, one thing to note, and that is, in our example here, we ignored y values. We have them in our mnist dataset. It has x and also y, the labels. These are the images. We ignored them completely. So y batch is not used. That is something that we have to be paying attention to, that this is unsupervised. It doesn't have a clue about what these images are. All we want to do is match. The output matches the input. That's what we really want to accomplish. And we are forcing these interim hidden layers, autoencoders, to understand what does it take to match this level with that level, output to input. And in completely ignoring the discussion about what these images are. We know what they are because it's a labeled data set, but we are completely ignoring this idea. So not used. You don't see any reference to y here at all. Having seen, let's go execute that. And this is your execution step. What we are doing is, for the epochs, 5 epochs, batch size 150, we are running it in that many epochs in batches. And so that's the function we'll run. And then we will have these output. So I'll run it myself also. So I'm erasing my blue ink. And I will execute step number 11 now. I need to, I think, import something. Something is an error. mnist not defined, which means I need to go back and run a step before here. I think I apparently skipped this step. So mnist not defined. Okay, I'll run that one. And it is now defined. So we'll go run our next layer, initialization layer, and then run number 13, which is the actual execution. As you can see, it is happening. Execution is kicked off. It is showing you almost high CPU. I have 4 CPUs, all occupied, almost 80% occupied. And this training MSE output is coming out. As you can see, 3 iterations have completed, 4th and 5th epoch, and then this training should finish. It has no idea what the actual images mean. We have not given it the Y value at all. The training seems to have finished. Let's see what happens next. So it minimized your error, essentially. That's what we just did. Training MSE is minimized. Now we want to see rather plot the outputs. So we'll throw some sample images at it and see what it actually creates. What does that mean? I think I must have confused a little bit, so I'll clarify what I just said. What I'm trying to say is, in this segment, what we are really trying to draw is, if I feed a number 7, what do you think it'll look like? That's what we are really trying to draw. So if you feed it this, it'll look like this from the output. Give it this input, it will produce an output that kind of sort of looks like what it thinks it is fed into. So if you feed this picture, it will produce an output that kind of matches the input. But mathematically, you can see that it doesn't match. I mean, I should say that this is lossy. It is lossy because it has like arbitrary things that are not here, in this segment, and there is some bits and pieces here, and some whiteness and some darkness that is not here, right? So that is pictorially the size. That's the right word. So pictorially, it is same, or rather similar. This is your output. This is your input. So pictorially, it is the same. Mathematically, it is not. See, there are lots of spots here that are dirty in that segment. I don't see any dirt here. It's all clean white. And I see some white patterns here in this segment, some whiteness here. That is not, actually there is whiteness, but I see some gray area here. That gray is not here. It's all clean. So the output doesn't mathematically match. Yes, the number 7 matches the number 7. That's not math I'm talking about. I'm talking about picture. And that is what you notice, is that the output attempts to match the input. Not exactly matches the input. The idea, this machine has no idea whether it is a 7 or a donkey. It has no clue, but it is able to reproduce and is able to actually create an image that looks like what you fed it inside. If I put Nilesh picture here, you will get something that looks like Nilesh, provided your data set is actually a set of people that look like people, or maybe, so actually you can feed any data set, any. But in this example, we are feeding it a mlai data set. There are mostly numbers. When you deal with people and images and more complex images than this simple image, which is just a 20 by 28 pixel set in one color, monochrome, that is a much simpler data. Whereas human being pictures or photographs taken by cameras are very complex compared to this. So that's why it's a different discussion. Having said, let us actually run this and plot what we see. So we'll see some reconstruction coming up. So I'll execute these steps here, which I think I ran this one. So I should go here actually, and then show the reconstructed digits and plot them. So it gets us something as an output. Now what we will see is that this reconstruction is, of course, similar to what you feed the input to be, but different. In that we are able to understand and create a system that encodes and decodes the output to match the actual input that you fed. And thereby we have some meaningful action that we can actually incorporate from these segments here. These two segments, specifically this and this, are the encoders that we are interested in, which is what we will actually, in a next step, extract information from here and apply to another example. Because this network that we ran did not have a clue about what we are feeding as an input. It doesn't know that this is the number 7 and this is the number 2. It just looks at them as a picture and is able to reproduce the same, I should not say same, similar pictures that look like that. That's the underlying concept. Output matches input. Output kind of sort of matches input. Not exactly matching, as you can see, they're not exact matches, but good enough matches. In fact, any person can tell that this is 7 and this is 7 and this is 2 and this is 2. It's unambiguous. Having seen this, let's see what else we have in this notebook for right now. I think this is the next example. So we should go back to the book right now. So going back to the book here and here and run ahead. So we just ran this TensorFlow implementation example in which we saw what we did, like, input, output produces the output that kind of sort of matches the input. Next, what we want to do is we want to, hold on, let me see what this thing is. Okay, this is tying weights. So tying of weights basically is to say that this is symmetrical. So that's the underlying idea. By tying your weights, what we are really doing is simplifying our math. Think about it like this, is that when we have, say, multiple layer network, is there a picture coming up here? No. So I have to draw the picture myself. So I will do that. What we have is this idea of tying weights. So move this one away, this one this side, and I'll draw the picture now. So tying of weights. The idea is if you have, say, a layer structure that looks like this, like our earlier example, pretty similar to our earlier example. You know that this is your W hidden layer 1, 2, 3, input, output. So the concept is we know that we want this to be symmetrical in a fashion. So when we know it is symmetrical, we can cut the amount of math we have to do by tying these guys together. Tying the weights. That's the underlying idea. Let's see in an actual example implementation, what does that tying lead to? What's the benefit? What's the point of doing this? The point of doing this essentially is that you tie the weights of the decoder layer to the weights of the encoder layer. That's what I just did here. This is your decoder layer, decoder steps. These are the encoder steps. Actually, these two are encoders. This is your decoder section, the rest of it on top. This is your decode section. This is your encode section, two of them. And so what we are doing is tying the weights of decoder layer to the encoder layer. That's a tie. And by tying, you're basically not doing any math here. And thereby you're cutting. And also cutting time, getting speed up, and also limiting risk of overfitting. Now in an example, it will look something like this. Weights number 1, you call them weights. Weights number 2, that's also calculated. But weights number 3 and 4, if they are similar, so if you want to draw a picture for this, it will look like W1, W2, W3, W4. They are symmetrical in nature, so meaning this is equal to that, and this is equal to this, and this is your input, and this is your output. And so what we are really doing in these examples is weight 1, we are doing the math here. Weight 2, we are doing the math here. Weight 3, we are not doing math. All we are doing is transpose of W2. So we are doing the weight W3, the transpose of W2. Transpose of W2. Weights from this segment. You're basically flipping it on the other side, transposing it essentially, and reusing the same weights from W2 layer from here. Same thing with W4. You want to calculate the weights for that layer, you will transpose W1. You take this W1 and transpose it and call it W4. So W1 is calculated, W2 calculated, W3 is transpose of W2. And W4 is transpose of W1. That way, what you're really doing is tying them together and not doing extra math. You're cutting down probably half of your work. And so easy to define, less taxing on the CPU, speeds up and reduces chances of overfitting. By the way, this transpose calculations and tying them together like this, you should do this only for weights, not for biases. So biases are individually zeroed out to begin with. So they're filled up with zeros. And then you define your calculations for hidden 1, hidden 2, hidden 3, and output, which are basically matrix multiplication of weights and biases. So this function is basically the idea of weights 1 matrix multiplied with X plus bias number 1. This second function is the same idea. Similarly, we have weights number 2 with input from hidden number 1 and bias 2. And this function is weights from number 3, input from hidden number 2, and bias number 3. And output is hidden number 3. So weights for number 4, output from hidden 3, and bias number 4. And so what we are really calculating is essentially step by step going through math and feeding this input to this layer, and then taking the output from this and giving it to this layer, and taking the output from this and giving it to this layer. That's what's going on here. If you carefully look, what this output is hidden 1. And you're feeding that output, so call it H1 equals, and you're feeding it right here. And you call it H2. And you take that and you feed it right here. And you call it H3. And you take that and feed it right here and call it out. And that's what you need to run it sequentially, essentially. Is you do one layer, then you do the next layer, then you do the other layer, and that's the underlying idea why we call it a stacked autoencoder. This is, by the way, the dominant approach. As you will notice that in our example, our W3 and W4 are not calculated. The transpose of existing weights W1 and W2. So this method is what is recommended for any kind of stacked autoencoder calculations that you will see in most examples. There is an alternative approach to doing that, by the way, and this is the alternative approach, which is unnecessarily complex. I don't actually recommend this approach. The other approach works out much more nicely in terms of understanding its meaning, which is, as you saw in this illustration, which is, just calculate step by step, one layer at a time, and calculate the weights and biases and move forward. And you fill up the whole sandwich as we go along. There is a variation to that. You can do that, which is this way, which is, I think it's a little clumsy to even think about that. It doesn't actually benefit in any fashion. It's just another way of accomplishing the same idea. And possibly it is done in our notebook. So let's see if that is actually implemented here. Tying weights is implemented. Let's run this. So let's go run the tying weights segment. So I'm going to invoke that now, resetting the graph and initializing, saving our state, and running our training. So training is running right now. And we are getting some MSE error out back from the system. And this should finish up quickly. Only 5 epochs, so 3 or 4 of them are already done. I think it did. So what we want to do is now is to produce the reconstruction of images. So we'll just run the reconstruction step. Excuse me. So the reconstruction, let's see how it prints. It should print just like we expect it to be. And that's what we see, the output, which is humanly similar, mathematically not. And when I say mathematically, I mean not the number 7 is not the number 7, but that the pictures are different from a binary perspective. But both are 7, both are 2. And that's the idea. And the next idea is training one autoencoder at a time in multiple graphs, which is I think this is the unnecessarily complex way of doing things, which is this picture that you see on the right side. I think that's this picture is what this illustrates in this code example. So we'll just run it and it'll actually produce the same output, but let's go execute that. So training, initialization, and training is happening. Oops, right there. And we'll wait for this to finish. This should be quick. And we'll of course get the same result. The point of this way of doing is just another way. It's not much difference from an actual end result perspective. You'll get the same result, but just another way of accomplishing the same task. So you draw the pictures and they come out to be exactly what we expect them to be. They're similar, but you will see carefully, if you watch carefully, they're kind of not exactly the same. Even the outputs are a little different. So look at this 2 here on the segment in this 2, and try to remember, see how it looks like in this sheet. When we do it again, it is kind of a slightly different too. If it's very hard to notice, but outputs can be different. Inputs will be identical. Outputs can become somewhat different because of the calculation might deviate a little bit. And okay, I think this is the convoluted way. That was the simple way. There are 2 ways. So the simple way was training one autoencoder at a time in multiple separate graphs. That was the simple way we just finished. Now the other way is to train one autoencoder at a time in a single graph, which is this on the right side. So let's go run that one also. It's not going to produce any magically different numbers, but just for the sake of running it, I'm running it. And here we go. So it's running training right now. And while it does, we can proceed ahead. It is unnecessarily complex way of doing this way. There is no reason to. There's no benefit from speed up perspective. Okay, let's see what we can visualize. I think we already visualized the results. We already saw them. So this shows us 2 numbers, 7 and 2. Say how they are similar to what the input was. Looks close enough. So I think this is something. So the autoencoder has properly learned to reproduce its input, but has it learned useful features? I think that's a good question to ask. What features do you see in this image? Is it a good-looking 2 or a bad-looking 2? Is it a cute 2 or not a cute 2? Who knows? That's the question we need to really ask. What features does this 2 or does that 7 have that we can tell that it's a 2 versus 7? And that's what we want to really get to. We want to understand what are the features that make a number 2. And we know that as a human being already, this is what a 2 looks like. So we have to have a half circle and then, something like that. So that's how you draw 2. But that's not the point. The point is you want to see what the autoencoder knows about the images that it looks at. And so does it actually know about the features? So I want to see and visualize what does it know about our features. So what I want to do is see if it actually does understand what do we have in the input image. Can it tell that this thing has a straight line or something like that? So some other weird stuff that you see in this features learned by 5 neurons on the first hidden layer. So that's a visual representation. We are able to produce the output by looking at the neurons in the first hidden layer and see what they see. And that is what they see is what you see right now here, which is kind of, to me, meaningless, except I see a number 4 here somewhere. But other than that, I see some patterns that maybe there's a white spot here and a white spot here. And I don't see much of interesting things. But apparently that neurons, the set of neurons in the hidden layer number 1 seem to get excited. And literally, I mean the word excited. Excited is the way to measure the level of excitement of a neuron. How excited it is about seeing this thing in the input. If it gets excited, its value will become higher and close to 1. If it is not excited, its value will be lower and close to 0. That's what I mean by excitement, is how neurons get excited. Is the values go close to 1 or close to 0, depending on the level of excitement they get about looking at certain features in an input image. Apparently, these neurons that we are looking at, these are the 5 neurons from the first hidden layer. These 5 neurons seem to get excited about looking at this picture, apparently. But again, it is visually hard for us to understand why they get excited about these patterns. And that's what we're trying to get to, is we want to understand eventually as to what are the things that identify and get a neuron excited. We can tell that, people get excited by looking at nice things. And so similarly, we want to find out what does it excite a neuron. We'll get to that soon. And so that's what we're really trying to find out, is that to help us actually, reason we are going that route of direction of discussion, is that it helps us identify features. And we will then use these features to speed up other work that we'll be doing, basically to help us detect what is considered an important characteristic that will actually get a neuron excited. That's what we want to get to. So we can then use that information to detect feature. Feature detection is a big amount of work in machine learning, where we really want to understand what features are relevant and what features are not. And if they're not relevant features that don't actually dictate the output, then we can possibly ignore them or not use them at least for now, and still get the answer that we want and still get the output that we expect. That's the underlying concept of detecting features, and we want to get to that. And that's this discussion about, is to visualize our features, is to see what the lower layers see and get excited about. What you will notice is that the lower layers don't tell us much, but the higher layers as you go will actually see what humans see, is that you will actually be able to tell that, hey, that's starting to look like a straight line or a circle or something like that. Or even higher layers will be capable of detecting things like, oh, that's a cat, or no, that's a dog, or that's Nilesh, or even higher order. That getting to a point of Nilesh or a person by its name, or his name or her name, is a even higher level item. A lower level would probably be human being. Oh, that looks like a human being. That looks like a dog. And then once you get to that level of feature understanding, then you can then further refine, okay, out of these humans, that looks like Nilesh, and that other is not Nilesh. And that's a next level of understanding. So the underlying idea behind feature detection essentially is to help us build a layered structure of understanding what constitutes good level of primary features and then secondary features and tertiary features, up to a point where we can then, by human eyes, detect something that we find interesting. Like I saw the number kind of looks like 4. Maybe it doesn't, maybe it doesn't, but I see some straight lines here and some straight lines here. So that may be a number 4, but who knows? So that's what I want to build my understanding towards, is to how these layers help me in detecting features in an input, so that I can make use of those underlying hidden layers and not have to train my system all from scratch. That's the whole point. When I have a bunch of pictures that I want to find out and train my image recognition system, and I don't have like the whole all the money that people have in large companies, maybe I have a small budget, I still want to accomplish, what I can potentially do is very, very cheaply collect pictures. What I need to do? I just go to Google and search, and I get a ton of crap load of nonsense pictures. I'll put them all together and run some machine learning algorithm on that. It will attempt to classify pictures in some fashion that will tell that, these type of pictures are different from those other types of pictures. It will still not be able to tell me what the pictures are. But then at least at the lower level of assembly of these features, to get me to a point where I can detect a cat versus a dog or a human, I can potentially use the underlying learning that the system has built me up to the point where I can detect that this is possibly a straight line or some interim feature up to that point. I can reuse that learning in any other system because I don't have to retrain my systems all the way from scratch. That's the underlying concept as to why feature detection is important. Now, having discussed that, let's go further in terms of identifying how can we use these autoencoders to what I call detect. Again, it's one more idea I've been detecting features, and that is the interesting idea here I mentioned here. That I think I should read that. So the idea that is interesting, at least to me, is a technique which is to feed. So you have a system here, for example. Let's go draw. There is a drawing here. So the idea is if you have a system that is an stacked autoencoder, so multiple stacks, autoencoder, output matches input. That's the encoder we have at hand. What I want to do is feed in some random picture. And I want to be able to run a separate algorithm that will help me identify when this neuron in a given hidden layer get excited. So the excitement level I will measure. What's the excitement level? I will like to measure that. And I will feed in some random picture. And I'll see what the level of that excitement of that neuron is. And I will, adjust this randomness a little bit this way or a little bit that way. And change the randomness or modify the picture in a fashion that will actually maximize this excitement. This excitement maximization. So this is the opposite idea of gradient descent. This idea is going to be gradient ascent. You want to get to the point where the excitement function for that neuron is maximized. And you want to train your system of giving inputs in a fashion that maximizes this excitement and iterate on it in a gradient ascent fashion. Not gradient descent, but gradient ascent. And you want to really get to the maxima for excitement of that neuron. And thereby you will adjust your random input according to what this gradient ascent algorithm will dictate. That will make you go to a point which maximizes the excitement of this particular neuron. And thereby, when it stabilizes, you will know that this particular random input that has evolved over time, because you gave it random number 1, and then you say, you know what, excitement level is 0.2. Okay, not good enough. Let's go adjust that and tweak that in backpropagation and try to optimize around maximization of excitement of a given neuron. And then you will feed in another input, because the gradient ascent algorithm will tell you to adjust your parameters of input in a fashion that will actually tend to optimize or maximize that number, the excitement level. And iterating like this on a variety of inputs, random number 2, random number 3, you will eventually land on some random input that maximizes the excitement of that neuron. Then you visualize this and see what that image was that excited the guy. And now you know. Now you know that what item or what input image excites that neuron. So you know now that, that's the kind of input detector that you have assembled together, because that neuron seems to excite this kind of a item. So now if you feed in that item, it'll get super excited. Any other item, not so super excited. That's the interesting find that I think I like, because you're applying machine learning gradient ascent techniques to change your input, to identify and study the patterns of excitement of a given neuron in a hidden layer, in a lower hidden layer, which is very hard to comprehend, at least for humans, to what makes these neurons get so excited about random crazy images that we have no clue about, like these things. Like we have no clue about what this thing is and why the neurons are getting so excited about, but we can actually come up with a systematic way of generating a random input that will eventually optimize or maximize the excitement of a given neuron. And then you can study the patterns of what inputs actually leads to excitement, which will help us gain insights on what features this network cares for. So we can then understand where can we use it. So that's the underlying idea behind, which is, I find, a very interesting proposition, because you can actually use these techniques in unsupervised pre-training. You collect a bunch of random things, feed it in the system. It'll tell you what features that it finds by itself without you having to label data manually. Because labeling data is a time-consuming, expensive, intense, boring, and pathetic job. It is designed to be given to Amazon Mechanical Turk. You may have heard me say that, but I think you may have. I'm pretty sure. Amazon Mechanical Turk is what's the word I like to use it? There is this thing called, they word it very nicely, but it's basically a sweatshop. The word is very nicely worded. This is a sweatshop. Another way to think of another company that does the same thing is Crowdflower. Is it Crowdflower? Yes. So the new name of this company is called Cloudflower, is called Figure 8. Is another way you can spend less amount of money, still money, but less amount of money to tag or label your input. So you can transform your text and images and audio and video into high quality, customized high quality training data. And so basically somebody will go and look and tell. So you go and look like a picture of a road on which your car is driving, and you look at the ahead, and there is this item here, some debris, and your car is driving on the road, and it is able to detect the debris on the road and is able to tell whether the debris is a piece of junk or a baby on the road. That's a critical decision, right? That you don't want to mess with. So you want to take the mistake of stopping the traffic, because you don't know what that thing is. And so you would rather stop and examine it and make sure that it is not a baby on the road. It may be junk, but you want to err on the caution and actually stop. But by detecting that it's humanly possible, machine cannot detect on its own. So you need some high quality training data. You pass it on, you take images of items on the road that you find and get help from people, like from this site, which is basically outsourcing it to places like India, for example, or other places, other countries. And there people will look at your images and tell and tag whether it is a junk or not junk. And it's a baby on the road, apparently, or some little dog in a blanket, or God knows what. So anything can be there. And so you want to really detect and correctly label, and you want to do this on an automated fashion for a self-driving car to detect that object and not make mistake, not make a a disaster mistake, which is going to be an accident and potentially a dangerous accident. You don't want to do that. So that's the reason why we need carefully labeled data, but you can cut down the cost involved in generating that by looking at ideas like this, which helps us in unsupervised pre-training of our data set. So at least the lower level features, you can expedite and speed up and reuse that data set from an autoencoder into a regular CNN or convolutional neural network at a higher level. You can keep using or reusing the layers from a autoencoder. That's the underlying idea. So unsupervised pre-training using stacked autoencoders. So here, the same idea I just said is described in the picture is this idea. So you have on the left side of this picture is the phase one, when you train the autoencoder using all the data that you have, whether you have labels or not, and you attempt to match the output to the input, and thereby these layers will be the encoders. And this is how you will decode the output and will match the input to begin with. And you will feed in random data or whatever data you have, all your data you have, just feed it. And it will then create this encoder steps. You want to copy the parameters over into your actual classifier, which will classify whether the item that you saw, the debris or whatever you saw, is actually junk or a baby on the road. You want to be able to correctly classify that. And you can do that by copying the parameters. You can just reuse them. Of course, the later layers or higher order layers, you need to train them. So you will train these through actual data that you have labeled. This is your labeled data input. This is all the data that you have. So all the pictures you see, just feed it. Whatever you can collect on the road, your cars are driving around, your test cars, you have them go around with people in there, so to control disaster. And you just have, you've seen probably or heard of, let's see what we have seen. You may have seen news of Google car, automated, Google automation. So Waymo's car, that's a Waymo's fully self-driving car. Then we have Google self-driving car. And just I'm picking up on self-driving, but here is, okay. This was formerly a Google, now it is a Waymo company. So formerly the Google self-driving car project is now Waymo apparently. So is it still a part of Google? Oh, we have to find out. I did not know this change happened. Apparently something happened. Okay, so the Waymo is apparently a new spin-off or something like that, some business transaction behind the Google self-driving car project. That was Google's car. Let's see some Tesla self-driving car ideas. You will see that these cars will go around. They are close to, this is another crazy news. Tesla stopped promoting the full self-driving option for its cars. Okay. This is like October 20th. A month ago. I must have missed that news. But this is the root of the problem, essentially. This confusion that he's talking about. This confusion is the root of the problem is that people are still expecting completely hands-free and fully autonomous driving from Tesla, and they're not getting it. They're not delivering on the promise. Tesla did say a full self-driving. In fact, if you drive a Tesla, you will notice that it will make sure that you put your hand on the steering. And if you take your hand away from the steering for like 5 to 10 seconds, Tesla will start yelling at you, literally yells at you, say, hey, I noticed that you don't have your hands on the steering. Put your hands on the steering back in quickly. Otherwise, it threatens you like left and right. Otherwise, I will disable automatic driving and you have to drive manually. It's a threat, straight up threat. And so that is what people find, that they're false, a little bit of a false promise right there, is that Elon did say it's going to be full self-driving, and people interpret it to be that I will just leave my hand away and let the car drive. That is not there yet. We are not there yet. At least for right now, it is not happened. And that's why apparently about a month ago, there's news that they have stopped promoting the full self-driving option. It is actually not full self-driving. And I drive a Tesla myself, so I know this is not completely full self-driving yet. I want it to be, but it is not there yet. One of the reasons why it's not there yet is it is not perfected yet. The system is not absolutely 100% perfect because of issues like this. You have baby on the road issue, which is going to be a major disaster for any company like Google or this Tesla or any of those. So it is going to be disaster. If you find a baby on the road and you run over the baby, you're dead. I mean, not just the baby dead, the company's dead. That's not what they want. So that's one of the reasons why they have apparently changed this promotion. It is not going to be called a full self-driving option because it is, yes, it did confuse me also. I was expecting it to be fully driven, but it started yelling at me. Say, hey, put your hands back on the steering. Otherwise, you know what? I will stop being automatic. And then you have to drive manually. And I said, okay, go put my hand back on. And that's how it works today. Having said, there is one more crazy idea that you should actually look at. And that is, I call it the stupidity of artificial intelligence, or it's natural stupidity. Let's put it that way. If you look at a road, a classic road, 2-lane. So this is the middle lane, and sometimes you will notice that the middle lane is dash 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 dash. It means that you can actually go on the other side, and you can also come back on your lane if you're driving this way. Occasionally to overtake somebody, or if the other guy is going slow, you can go like that. If it is a dashed area, that's the underlying concept. Now, if you have seen a 2-lane road in which there'll be portions in which there'll be double lanes and one side will be dashed, which means you need to go straight. You cannot go this way, not allowed. But this guy can go this way and go back. That is allowed because the dash patterns. You have a straight line here and a dash pattern here. So that's the pattern. You already know this. So this is common knowledge. This is the law. Having said the stupidity now. So imagine a situation when you have an area like this and area like this, dash patterns. And so now you have your Tesla car and it looks that, hey, there's a dash, so I can go in. It goes in. And then the Tesla is here. Now what happens? Now that stupid Tesla is stuck because it cannot go out. You see that problem? So this is a classic, what I call follow the rule, dumb. I can come up with names for these things, but essentially that's a problem. If it was a human being instead of a Tesla, the human being will already know that this is a trap and it's okay to not follow the rule. Not being dumb. Don't have to be dumb. Don't have to follow the rule because this is a trap situation. You can totally comfortably drive out. It's not a problem. And that's human knowledge. Machines are not there yet. So you can actually put a Tesla in a trap like that and it will get caught. It will get stuck. Unless you intervene and you drive it out, which is totally possible. And so that's the state of affairs today. Having seen that, there is actually one more thing. Maybe there's one more company which is said to be doing it. Minor crash. No pictures. I was expecting pictures, but see the number of cameras these guys have compared to a commercially available car, which is not this, by the way. This is a Lexus, and commercially available cars don't show or expose their cameras like this, but this is a test situation. So you have secret self-driving cars going around, basically collecting data, and collecting the data that we are using as our input right here, unsupervised pre-training. That's the segment. Whatever you collect from all the cameras all around the periphery of a car, you will capture and use that as a basis for unsupervised pre-training, and the initial steps of your training is where this thing comes in handy. So that is the interesting use case from unsupervised pre-training, the underlying idea, which is what you saw, copy parameters and reuse that in other algorithms that you will have. The concept is that you have, because building a large unlabeled data set is cheap, but building a labeled data set is time consuming. So it's quite common to have only a few thousand labeled instances. And so you can potentially create your own private convolutional neural network and run it on your own photographs. In your library, in your computer, you might have like maybe hundreds of thousands of pictures you might have over the years. You label only some of them as, this picture is Troy, and those pictures are your friends and family and other. You label only 1,000 of them, and you can use, just by these 1,000 labels, you can actually create a convolutional neural network that looks at your own image collection and correctly classifies all the pictures containing Troy, all the pictures containing other people in your family and friends and all that. That will happen. And you need to apply these techniques like we're discussing right now. It is not necessary for you to label each and every picture, because that's pointless and actually not doable. It's quite boring. Asking you to label like 70,000 pictures. I think I have like 157,000 or some pictures in my collection. It is humanly impossible for me to label them. So I have labeled some, and I use other techniques, mostly from Google Photos and other algorithms that I have attempted, by the way, this myself. I have also attempted another neural network on my music collection. My music collection is mostly Indian music, but some music of which is I call it Western music. Maybe I should change my way of saying it, but at least people from India will call the music that you hear as Western music, and the Indian music is called music. Like I call Indian food, I call it food, as opposed to you might call it Indian food. So that's the way to describe. But having said music collection, I have classified it, and it listens to the music patterns and is able to detect similarity, identify artists, connect with metadata to get from other sources to identify who the singer is and all that. So it's a detailed project, which I'll talk about that later at some other point in time. Let's see. The reason why this whole thing that I'm mentioning here about label only a few and leave the rest as unlabeled is actually the reason why this deep learning thing is like blowing out of proportion. Everybody's doing it, is because it is possible to do it now. And that was actually discovered by this guy. in 2006. Before that, people assume that you have to label every single data set that you have already, and then you can apply that to a training algorithm, which will then learn, and then you use that algorithm to predict for future data set. That was the thinking, and that was changed at this time. The essence of the discovery was that you can actually pre-train your network unsupervised. That's the discovery that Jeffrey Hinton did in 2006. And ever since then, this deep learning is blowing out of proportion. And they did not use this autoencoder techniques. They have a different technique called restricted Boltzmann machines. It's a different algorithm that they used, restricted Boltzmann, which I think it's a reference here. So different algorithm, but autoencoders also work the same way. So that's the autoencoders are more popular, more effortless compared to these, and that's why people use autoencoders, not that. But it's an option. So this is an option available. Autoencoders is another option which is dominantly useful. And the reason it is being used is because it makes it possible. Makes it possible to pre-train your data set without having to manually label, which is an immensely boring, if not expensive task. Okay, core idea is to remember this. Copy the parameter. Excuse me. Give me a second. Core idea is to copy the parameters of lower level hidden layers from an autoencoder that feeds all the data and use that, and don't change it. Keep freezing it. Freeze it. Only the upper layers you want to train. You can reuse the layers from here. And this is on unlabeled all the data you have. Don't even bother about the Y labels. Just focus on the X data set and ignore this. Feed it, and it will match your X. In the process, it will learn these parameters that we are interested in, and you use them here. And then you will do whatever you want with your labeled data set. So these upper layers will be trained on the labeling. So it will then detect whether it's a 7 or an 8 or a 2 or whatever. In the lower levels will detect those patterns of this or that or whatever, horizontal line, vertical line, this pattern, that pattern. God knows what patterns it comes up with. God knows what those neurons get excited about. But actually not God. You can actually tell which image excites a given neuron by doing gradient ascent technique. Okay, let's go forward. So this extension of the idea of simple stacked autoencoders. The ideas and some variations to that same concept as you will see in subsequent examples that we will discuss. One of the ideas is to have a method that will reduce noise. And what we are doing essentially is inserting noise and forcing the autoencoder to reduce it. So if you look at this image, let me grab that. Yeah, here. So here, you get an input, you deliberately add some noise and force this output to match the input. And that's one approach. The other approach is the other side. You have an input, you deliberately create another scenario, which is kind of like noise. But what we are really looking at is using the dropout function, which is, like half the neurons, you say, I don't care, ignore them. And you still proceed forward. And thereby you're giving it limited information about. So it's kind of noise insertion in some sense here, similar to this idea. You're actually adding noise to the input and forcing the output to match the input. Thereby these layers will learn to eliminate noise. So you have some noise inserted. This will basically go minus Gaussian noise. It will subtract the noise and produce the output that you expect. So this is figuratively speaking. Same idea here. You insert dropout and you have the output that matches the input, and you train these layers. Again, here, these layers are essentially reducing the noise. And that's one of the ideas here in this extension of your stacked autoencoders. And so let's go read a couple of things here to make sure that I don't miss any important ideas. And one of them is to add noise to input and train it to recover the original noise-free input. So you have noise-free, you add noise, and you expect noise-free output. That prevents the autoencoder from trivially copying its input to output. So it ends up finding patterns in the actual meaningful input and thereby learns how to reduce noise. And it is mentioned in a thesis. So this guy's website is, by the way, beautiful. You should take a look at that. I think we saw one time in one of the sessions. You should absolutely make a note of visiting this guy's website. It has lots of examples that are phenomenal, to say the least. So noise can be pure Gaussian noise or dropout. I think we discussed that, so I'll proceed forward. Just don't want to miss concepts. And there is an implementation of TensorFlow. So let's see what the implementation is going to do. We are going to use the dropout version as opposed to noise version. But where is it implemented? Visualizing extracted features. So this is unsupervised pre-training. Why didn't we run it? Well, we should run it. I think it was not mentioned, or I must have missed. So I think some of these sections we did not run. So I'll just quickly run them. Cache the frozen layer outputs. It has no reference in the book, apparently. But this idea that's going on right now is caching the frozen layer outputs. And the idea is that we want to reuse. So the frozen layer outputs, we want to save that. And the saving step will essentially make it useful in another network, another neural network. So we are reusing some of the components, we are caching them, freezing them to use in a different network, which is going to be this. So this is the save state of the lower layer. Now, having run this, let's go run the next step. So we'll reuse that. So the reuse is happening here. This is not mentioned in the book, apparently. So this is your save function here. This is your restore function right here. I think it's not mentioned in the book. That's why I missed it. Restore functions are going to run. First of all, begin a session of TensorFlow. You restore your learning that you have, my model one at a time CKPT. This is the capture. And you're reusing. It says not shown in the book, which is why I missed it. And then we are able to re-visualize the same reconstruction, but reusing the underlying training. That's what you're seeing: plotting images, digit index, example images 7 and 2. printing out, clearing this, and running the visualization reconstructions like this and like that. Now we can visualize our extracted features from the same restore. We will take that and extract the interim features in there to see what they actually contain. And we see that they contain something that looks weird to humans, like this. We cannot really tell what this thing is, but apparently these things excite some of the neurons in the lower layers. We have no idea what that means, nor do we care. But what we care about is that we know that these things get excited by those images. And the underlying concept is to be able to save and restore like this, to reuse unsupervised pre-training. That's the concept. So going on ahead further. We have our, did we run this? Create a small neural network for MNIST classification. So this is regular without pre-training. And this is with pre-training. Yes, so both of these examples are available. So both examples, the first one is without pre-training here and reusing the first two layers of autoencoder that we pre-trained. And so that is your pre-train action, save or restore action. So we'll get to that. But first we have to run the without training portion. Before that, we have to run the initialization step. So it is up ahead here. And so this is your example of how do you restore an interim lower layers and reuse them. So we are going to create a small network for the MNIST dataset. We have the layers that we had in our earlier example illustration, something like this. Yeah, this is a good way to think about. In our example, we have 784, 300, 150, 300, 784 neurons. That's this idea here, 784, 300, 150. Number of outputs is 10 at the final result, which is here. Learning rate, L2 regularization, activation function, ELU, L2 regularization as our regularizer, our initializer. Then we have the X placeholder, the Y placeholder, number of inputs coming from here. We have weights, N1 hidden. For the inputs, we have weights 2, weights 3, weight 1, weight 2, weight 3. We are defining them. We are setting biases as variables, 3 weight variables. Then we are setting hidden 1 within, X matrix multiplication with weights 1 to calculate hidden 1. Is using hidden 1 here and multiplying with weights number 2, matrix multiplication and biases, and then using that input here, hidden 2, multiplying with weights 3, biases 3 added to get the logits. The logits are the output function. We'll calculate cross entropy function, the regular loss, which is just your weights, the regularizer. I think this, I need to erase this to move my screen. I'm going to erase my blue ink. There is something written on the other side here. I need to go read that. Okay, so the regularization loss function, I think I should just shrink it. Yeah, that should do it. So this regularization loss, we are going to add our losses together, the cross entropy and our regularization loss together, and optimize on the loss function. Then we get the answer for correct. What's the correct value using Y? The accuracy calculations, and we will initialize, and we'll also have a saver state to save the state of weights and biases for 1 and 2. And we'll define a saver function. So we'll execute this portion and then run session, a TensorFlow session, in which we are this time running without any pre-training. So the whole data set goes through. Number of epochs, batch size, and only 20,000 labels instances in this example. And we run the session and we calculate its accuracy evaluations. Test accuracy is coming out to be about 94.92%. Now we are going to reuse the earlier that we saved here. That's a save session state. We are going to restore that right here in this step. And we are going to restore that and use it in our later layers. So as you can see in our later example, we don't have all those interim layers because we are reusing our pre-training, interim pre-training, or I should say unsupervised pre-training in this example. So I'll run this example again, and it begins with restoring the parameters from our earlier save in a earlier run here. And it finishes a lot quicker because it doesn't have to do much. Comparatively speaking, you can actually time it how faster this one is, or rather how faster this one is compared to that run over there. And so that's the underlying idea behind reusing or unsupervised pre-training data. This idea here, copy the parameters. So we are basically saving it and reusing it in this example. Let's see stacked denoising autoencoder. This denoising means you have to have some noise inserted. And so we will use the concept of a dropout in this, I think. This is the dropout example, is it? Yes, this is the dropout example coming up. So we'll actually insert, which is this one. So there are both examples, I think, called out in the notebook. In here, we are talking about two different ways: the Gaussian noise inserted, dropout deliberately inserted into the input, and we see how the outputs match the input. And so the first example in our notebook on the left side is going to focus on inserting Gaussian noise, which is this example here on the left. And I will run that. But before that I run, I will like to read it. And so I'm going to read this segment up to this point. So this is the second one, which is using the dropout on the right side. So we'll first run the Gaussian noise, understand it, and then run the dropout function also. So the first one, denoising autoencoder using Gaussian noise, reset the graph, inputs, layers, and you can see that this is matching your 3. 3 is matching 1. So there is you're basically symmetrical in its nature. You want to match your output matches your input. That's also symmetrical in nature here. That's what you're really trying to accomplish, is that our network becomes symmetrical like this. Even though we add a noise, we'll now add the noise element. Before we get to that, we have a learning rate calculation, noise level number 1, just a factor. We can multiply that with number 1. We can adjust our amount of noise we insert by changing the noise level. This is number 1. You can make it 2. You can make it less than 1, 0.5, any number you pick and choose. How much noise? That's this noise level, which you multiply with a random number and you add it to the input like that. And that's your noisy input. Then you define 3 hidden layers, 1, 2, 3, and output layers, and reconstruction loss. This is your mean square error loss between output and X. Square it and mean it, MSE. And then you run your optimizer and minimize the reconstruction loss, which includes the MSE aspect. Then you also define a saver function. Now we will invoke it. This will actually run the session. So I'll erase my blue ink. And first of all, reset the graph right here. Then I will set the item number 34, which is this one, the one in blue highlight on the left side. And then I will set my initializer and saver functions. And now I'm ready to run. So the run will happen in 10 epochs. And I will execute this item now on the left side, blue. There it goes. And it is running right now. It will run 10 epochs, 150 batch sizes, and it will also produce our mean square errors. The loss calculation that we are doing, it will print them out across 10 iterations in batches of 150. And you can see the computation happening, CPU chugging along at 80%, 75%. And this calculation should finish. What you're looking at is, even though our input has been distorted by inserting some noise, we did insert noise deliberately, which is right here. I'm adding noise to the input to make it noisy input, and using the noisy input right there in the first layer, and then goes on all the way to the top to match the output, matches the input, and minimizing the error function. And that's what this calculation leads with our saved state. That was using the Gaussian noise addition method. So just deliberately insert noise, and your network will attempt to cut that noise. So even if you have noisy input, it will still be able to detect the actual input that you wanted to send. So that's the one approach to denoising autoencoders, to reduce noise from data or signal. The next idea is to run the same approach using dropout functions. So this applies. I'll now go and read that. So we understand, excuse me. So we are defining the same set. Again, inputs, hidden 1, hidden 2, matching to number 1, this matching the input, and our learning rate and dropout rate. Usually we have seen 0.5 dropout rate, but that's just any number you can choose. Of course, don't use the number 1 because it will drop everything. That will be a bad idea. So 1 is not a good idea, but anything less than 1 is a okay number to use. Dropout. We are setting our training placeholder with default X as an input. Now we are creating a dropout X, which basically sets the dropout rate on X, which is this idea here. Input, dropout. Then we are defining the usuals. Hidden number 1 is basically using the input as X drop is the input here. Hidden 1 goes in here. Hidden 2 goes in here. Hidden 3 goes in here. And then you get the output. When you have the output, you measure it against the X input. You measure it, find the difference, square it, mean square error, minimize it. And that's the minimization happening here, not here, here. And initialize and create a saver function, then you actually execute in the session. So this is initialization steps. The invocation happens here. And I will clear my blue ink and actually run these things. On the terminal, we see it on one hand, and I will erase my ink and make this tool go away. And now we'll run the dropout portions. So dropout, run to reset the graph, set some variables, initialize, and run. So running is happening. And what you will see is what you see is that it is actually, even though you're applying dropout to the input, it is still attempting to match the input in its output. This output is going to be matching the input, is what you see in these results. Both ways, Gaussian noise insertion or dropout function. So both options. By the way, dropout is the one that is likely most people use that version. Deliberately inserting Gaussian noise is also okay, but people just prefer dropout. So that's the example mentioned here, the dropout examples mentioned in the book. That's what we are running right now. And the run finished, which means we should be able to examine the reconstruction based on the my model stack denoising dropout. The same dropout CKPT is the save state, is using the save state to reconstruct our digits to see what that was. So 7 shows like 7 and 2 shows like 2. And that is your execution step. I just executed this item 46. Now we'll go to the next idea, which is sparse encoders, sparse autoencoders. And that requires a little bit of discussion. I think it is not super complex, but something that is just a little bit of different kind of math. Nothing much. So the math is about the difference in math is mean square error function. You already know you get the output minus input square, mean it, like that. And that's your mean square error, and divide by n. And so that's your mean square error output. That's one type of math, MSE. There is another type of math to calculate error functions, and that is this math. So one is this calculation, MSE calculation that I just showed you, which you already know. This is a different math to calculate basically error function. The reason we go this way is that because it has much stronger gradients than mean square error. And so this other math that you will see now, it's actually down there. I'll go to that page soon, is different from this math, which is easy to understand. And we already know this is going to be a different kind of math to calculate basically the difference, out minus x, out minus in, difference. How far away are they from each other? How much is the error? How much is the loss? That's the calculation. And we can do it in a variety of ways. MSE happens to be one of the ways. This is just another. So here it is. This is the math. If you look at the math, it is right there. There's a log function involved, and that makes the derivatives a little bit easier to calculate. This as some, I think the underlying detail behind this is mentioned in an appendix, I think. Or where is it mentioned? Chapter 4? Briefly discussed in chapter 4, huh? Maybe it is mentioned there. So we should go and take a look at that later. But the concept is, it is just another way of calculating difference. And so that's the underlying idea that we will be using to discuss this type of different type of, just another kind of constraint. What we are really doing in all these autoencoder business is we have an expected output. We are giving it an input, an expected output. We want it to match the input, and we are putting arbitrary constraints. We saw a couple of them already. We saw that we are narrowing down the shape of our neural network to deliberately constrain it in the middle to make it learn the real meaning in the data that is coming in so we can reproduce it. We also had other types of constraints. For example, what we did was that we inserted Gaussian noise. So Gaussian noise inserted, and still we find that output can be detecting the input that was given to begin with. We also did some dropout ways of creating constraints into the system and thereby forcing the system to really learn what the patterns are in the data so that it can actually faithfully reproduce almost equal to the input, not exactly, but almost equal to the input. And that's why we are, putting various types of constraints in the system, in our system, that will attempt to what the input was, even though we are deliberately creating hindrances or constraints in the system as we change variations to the concept of a simple autoencoder, which is as simple as y equals x. This is like the silliest autoencoder, y equals x. That's it. You give it an input, well, that's the output. There's no encoding, no decoding business. It's just silly y equals x output versus output equals input. That's the silliest autoencoder you can get. But we are not interested in getting silly. We are interested in finding out the meaning in the data that we are feeding in, and that's where we are inserting constraints. And so this is another constraint, sparse. And what we are really doing is creating sparsity in our neurons. What we are really doing is we are, keeping only those neurons that are significantly active and ignoring everything else. So what we are really doing is, for example, this is an example, to have an average of only 5% significantly active neurons in the coding layer, and every other neuron will be shut off, thereby making it sparse. So you have a layer of neurons in the hidden layer and the lower layers. Only 5% on an average of those who are active will be used, and everybody else will be zeroed out. And thereby you are creating a sparse autoencoder. And this is another way to constraint. And just, you will see more variations of the same idea over and over applied. Input, output tries to match the input, and a variety of constraints in between, like this type, that type, various variations to this. And this is the way of inserting constraints. So we are forcing our network under the hood to learn patterns in the data. That's the underlying idea. Having said, when talking about sparsity of neurons in the layers, in the hidden layers, what we're really talking about is the idea here, which is if you could speak only a few words per month, you would probably try to make the most, or make the words that are worth listening to. If you had this constraint, artificial constraint, that you can speak only a certain number of words per month, you will be very careful in choosing the right words, only the ones that have real meaning, and you will want to communicate using those words, and thereby forcing yourself to function in a fashion that will detect most important, most useful things that will communicate. And that's how you would think about sparse autoencoders. This is just a way of thinking. And yes, in our sparse encoder calculations, when we try to calculate our loss function, you will use this method of calculating losses. So different than this method, which is mean square error function. Having seen, let's proceed ahead. And there is this TensorFlow implementation in our book. So we can see that on the left side, the actual implementation. So let's go see the sparse encoder implementation itself that we are looking at on the notebook on the left side. And it also produces the same expected output. Like all the examples are basically running the same expected output produces the 2 based on the input that you give it a 2, and produces the output 7 based on input you give 7. Input image is different, but the output image is conceptually a 7, even though it looks from an image point of view, it is a different image. So let's go run this sparse encoder. But before that, read it. So reading that is essentially this calculation, which is somewhat different than our standard mean square error calculation. And that is this math, which is what you see here. This is your, what's this guy's name? K and L, the two guys. Yeah, the Kullback and Liebler divergence. That's this Kullback-Liebler divergence calculation. We are setting a p-value and a q-value and calculating mean square error also, which is p minus q to the power 2, and plotting a bunch of things, saving the figure. This is what you see, comparatively speaking, mean square error, and the KL divergence error, which is this line, and that MSE is that line. And this is your actual sparsity versus cost function calculation. So just trying to compare how the two look like, basically to help you understand the difference in the two approaches to estimating error calculations or divergence calculations. You can see that this has a steeper line compared to the red line here. Steeper, less steep. So higher, what I call gradients. Higher gradients means faster convergence in this context. So now we'll begin to create a graph, reset it, and run our TensorFlow session. So we'll see what that involves. Reset the graph, provide an input space, and this space is 1000 hidden 1. Output matches input. So our layer is only one in between with sparse encoding. We define a function and that returns the divergence itself, the same divergence function here. We are setting a learning rate, a sparsity target, sparsity weight, and input defined as the number of inputs, hidden layer, and output. Hidden layer calculation is based on input, and hidden one, which is 1000, and activation function we are using is sigmoid function. This is necessary. It is not shown in the book, but the underlying idea of using a sigmoid function is that you want to make sure that the values are not actually 0 or not actually 1, but somewhere in between. And you can very easily accomplish that by using a sigmoid function, which is, looks like this. No, hold on. It looks like, it is never 0, never 1, but it's somewhere in between. And that is the reason why we want it to be not 0, not 1, because this calculation, if these numbers are 0 or 1 exactly, then it will lead to not a number error, because it is basically divide by 0 situation. Divide by 0 right there, or divide by 0 right there. That's what you will run into. And so you don't want to run into those, and therefore you want to use sigmoid function, which is a natural choice, because otherwise these guys will run into divide by 0, not a number scenario. And you don't want that. That's why we are using the activation function as sigmoid. And output layer defined based on hidden one. So this input goes here, this X goes here, and then you calculate the mean, calculate sparsity loss, calculate reconstruction loss, and your total loss function is a total of reconstruction, sparsity weight times sparsity loss. Your weight is defined here. Sparsity target is 0.1, which is what you want to target at. You define, use the Adam optimizer and try to minimize your loss variable, this variable, and you want to now invoke a session. So you will initialize, save the state, 100 epochs, 1000 batch size, and you will run 100 epochs. So I'll now run it now and let it go. So here we'll reset our graph, define our KL divergence function and set up these variables, initialize state, and run. So it is running, doing it close to 100% CPU on 4 CPUs. And it will eventually find out that 7 looks like a 7 and 2 looks like a 2. So that's not interesting. We have seen it many times. So we'll proceed ahead. It's running. We are looking at the TensorFlow implementation and we are running it right now. So now there are more changes or more ways of putting constraints on our autoencoders. And those are probabilistic autoencoders and generative autoencoders. Let's go see what those things are and see how we can use them. So this, I'm going to put it behind in background, and that thing, I'll let it run while we look at our variational autoencoders, which is a recent thing, about 2014. It's a recent thing. And apparently there's a hyperlink there. So the book has a lot of hyperlinks, by the way. If you haven't noticed, many of these items in the book are actually very good links. And so it's a good idea to just go and inspect them. And apparently it shows when I click on that it doesn't seem to open anything here. But actually there is. If you go and pay attention to the download section, you just saw that I have this thing downloaded, which is the paper published in 2014 by these guys, which is what these guys are. It has quickly become one of the most popular types of autoencoders called variational autoencoders, and this is a 2014 paper. So we are not reading the paper right now, but I recommend that you at least take a look to see what you find. I'm closing it. But definitely make a point to go visit hyperlinks in the book and run through a bunch of things and exercises, lots of exercises we need to do. And by the way, if you're doing these exercises, please ping me and I'll do it with you. Anytime. I'm here. I am so highly interested in this that I want to actually do it with you. So if you're in the mood of doing an exercise even after the bootcamp is finished, ping me and I'll do it with you anytime you feel like. So I have that offer to you. Come online, just do a Zoom conference on the fly. Whenever you feel like, hey, I have some time, just text me or Slack chat or whatever, and we'll come on Zoom and do it. I'm most of the time I'm here. I'm not traveling. So I would love to do it with you. If you're doing exercises, ping me. And remember to do that. And so let's go further with our variational autoencoders is to see what they mean. And it's easier to just look at the picture to understand what they mean by this, because the pictures will tell a lot quicker. So here is the idea. So what we are essentially talking about is a hidden layer that doesn't compute an exact number, like a deterministic value or I want to output this number. That's not the idea here, but a slight variation to that. The variation is that it is going to produce output that are determined by chance. Even after training, it is partly determined by chance, not completely determined by chance, partly. What does that mean? It means that, in any of these runs that you will see some output like this based on input like that. I put a 7, I get some 7. That's a visual output for a visual input. In other cases, you might have a number input, some number, and you expect the output to be a number, some number. That is very deterministic and very, very clear that, I feed in a number 0.2 and I get the output as 0.2 or maybe 0.21. That's a very definite answer. That's the output. You got that. However, in this type of variational encoders, the output you get can be a statistical variation around some point. What does that mean? It means that you will have a point and it will have a distribution to go along with it. It can be anywhere in between here, all these points, and some distribution. So it can be 0.21 if you like, but it comes with a sigma. It comes with a standard deviation. And of course, a mean value, 0.21, this value. It also comes with a standard deviation to go with, because it can be a little bit of 0.22, or it can be 0.20 or 0.19, or it can be all over the map. That's the underlying idea, is it is by chance, partly determined by chance. Let's go do it one more time to clarify this idea very, very clearly. So this white sheet of paper is what I need to bring up. So I need to bring this white sheet of paper and like that. And so what I'm talking about is the idea that you have some input and you want to produce an output. You want to match the input, ideally exactly. In cases, most of the time, it is not exact match, it is approximate match. And so for an input of 0.2, you will receive an output of 0.21. That's a deterministic encoder. All other examples up until now were deterministic in nature. You get some number. That's the output. In these types of variational autoencoders, you don't get a number, but you get a range of numbers. Let's put it that way. I think that's a better way to say that. So this line here is basically saying that you will get a range of numbers, which is kind of sort of around 0.21, but it comes with a distribution of some sorts. So probabilistic distribution. The number can be anywhere, like 0.18, 0.19, 0.20, 21, 22, like that. And there are some chances of these numbers can be all over the map. And of course, this means that there is a standard deviation that goes along with the mean value. The mean value is this. And so that's the idea of chance, determined by chance, that it can be all over the map. 1 sigma, 2 sigma, 3 sigma, 4 sigma, 5 sigma, 6 sigma, and like that. These are sigmas, which is standard deviations. How many sigmas away can the number be? And of course, 6 sigma is like way, way out, very, very rare possibility, but is a possibility. This is the mean, meaning very likely possibility, where it's not always the number, it is a possibility. And so you got sigmas, 1 sigma, 2 sigma, 3 sigma, like that, away from the mean, that becomes rarer and rarer. And so is the other direction, rarer and rarer on the other direction, 1 sigma, 2 sigma, 3 sigma, like that. So what of that probabilistic nature of the output is the idea underneath variational autoencoder, which is how reality is, by the way. It's not exact, it is approximate. In real life, you will see most most things in life are actually probabilistic in nature. In fact, that's how even we speak. Are you going to, like, if you talk in human conversation, are you going to come with me this evening? And people will say probably, meaning they're not sure. You will never hear people say, are you going to come with me to the movie? Yeah, probably I'll come. That's our common language is also like that. People say that. People don't say, I will definitely come with 100% guarantee. People don't speak like that because that's how nature is. It's probabilistic. And so this idea of being probabilistic in its output is the concept of probabilistic encoders, which determines that the output is partially determined by chance. Not completely, but partially. And that partial determination is the underlying idea which produces a mean and a standard deviation. There's a mean, standard deviation. So two outputs come out from here. There is some mean value, the standard deviation value, which is this mean value, and then some STD value. So it goes this way or that way. It can be anywhere on the map here, somewhere on the bell curve, I should say, not the map, bell curve, depending on chance. And that's the idea here. So it produces the output. What you can also do is insert noise into your standard deviation to make it even more noisy, and thereby setting constraints. So from a visual perspective, if you see this input space, if you provide that input space, it is kind of attempting to match the input space in the output space. So output matches input like that. However, in the coding space, you will find that there are these mu, or rather, I should say, clearing my drawing, I should draw this mu, this blue dot maps to this. And this circle is this, is the range of variation that you might have, an approximate like 2 sigma, 3 sigma range away from the mu is how I would draw this on a two-dimensional coding space, which shows me the distance of variation of the actual intermediate step as the output of this layer, is a way to create another constraint in this stacked autoencoder, which forces the output to match the input, even though we have some nature of chance built into the system. That's variational autoencoder as an example. And an example of an instance passing through it. So this is the input space, this is the input data that transmits to. This input data transmits to that data here with a probability distribution around the circle here, approximately shown as by maybe 2 sigmas or maybe 3. And this translates to that point here, which translates to this point here in the output space, which matches this, by the way, exactly, or approximately, depending on how accurate your systems are. It's mostly approximation, by the way. And that is the idea underneath our, what's it called? Variational autoencoder. The good thing about these types of autoencoders is that they are able to generate new training data. Artificially generate. So it will basically become a dude who writes 7 like this or like that, or maybe like this. I don't know how people write, but I'm just attempting to draw 7 like humans do. 7, 7, 7. I don't know. I'm just making stuff up. And that's exactly what this guy will do. Generative autoencoder. It will generate new instances that look like they were driven from people, drawn by people. So it will generate new instances that look like they were sampled from the training data. That's the underlying idea. And we'll see this in I think there is an example. Let's go check whether there is an example for that or not. But there should be one. The training seems to have finished, and we should be able to run this last step. So that should produce the output. 7 looks like 7 and 2 looks like 2. Yeah, here it also mentions the idea that I mentioned already, which is use sigmoid function, must output 0 to 1, which is why we use sigmoid activation function. Otherwise, we'll get a not a number error, 0 to 1. And then I think we are getting to the variational autoencoder examples. So we'll get to that point after we finish this segment. Run, 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 and run. And then get to variational autoencoders, in which we will have, I think we will have, there's a generation digits. Yeah, there is an example of generation. So this is going to generate example input data that looks like people drew this. So let's go see this. This is interesting. So let's go see, first of all, the idea behind variational autoencoder as an example illustrated here. And then we'll also go look at our generative autoencoder idea, which is it will generate pictures that look like somebody had hand drawn the pictures. That's a generated output, by the way, not actual people drawn pictures, but machine drawn pictures that resemble the input training data. So basically you're looking at generated data. That's a possible use case of generation of new content. If you need to have that, that's an ability that we get with this variational autoencoder example of constraint. It's a constraint example. So now let's go run this segment. Variational autoencoders, what are we dealing with here is this picture. Where is that picture? Down here, I think, this picture. That's what we are really dealing with. And let's go read that. So here we have our graph reset. We are importing partial from functools. That's an import from Python library. Input image 28 by 28, 784. We have 500 here, 500 here, and 20 here. This is our coding, the encoder coding right there. This 500 matches this. This 500 matches this, which in turn matches this, and this matches this. So it is 500, 500, 500, 500, 20, 784, 784. And this matching 2 with 4, which is this one. And this is matching 5 with 1, which is this one. This is matching output with input, which is this one. And learning rate 001. That's a chosen rate that we have picked. We are defining an initializer, creating a TensorFlow dense layer with activation function elu activation and initializing the dense layer. We have X as an input placeholder with number of inputs from here. Hidden 1 defined uses X right here. Hidden 2 defined uses hidden 1. Hidden 3 defined. Now hidden 3 is this guy. And so here the definition of this is slightly different. You can see that the hidden one has 2 items. So this is the mu item, this is the sigma item. The mu is for mean, and this is for standard deviation. So 2 items defined here, mean and sigma. And it is essentially based on input from 2. So it gets input from here. So this gets the input, this gets also the input. So 2 items there. And here is your n hidden 3, which is the count for number 20. And activation function is none. Noise, we are inserting extra noise from outside, adding that noise, random normal distribution noise. And this shape here basically means that we have 20 such items. So the hidden 3 sigma is the shape of that, is what we are adding to the coding function, multiplying it to that. That multiplication will happen right here with noise. That's the multiplication happening, this one. Then we are calculating hidden 3 output based on the summation of mean and sigma with noise. So this summation is basically the mean and sigma multiplied by noise. Add them together to produce this. And that's the output from hidden 3. That gets fed into hidden 3 here and to produce a hidden 4. And then hidden 4 gets fed into this to produce hidden 5. And that's what we have here coming up. Then we have a logits function defined, which is the last layer. Hidden 5 taken as an input. So this item taken as an input. And the final output is a sigmoid function on the outputs. We define an entropy function, which has the logits as input. We define our reconstruction loss to reduce the entropy, the cross entropy function. And now we are choosing a very, very small, tiny number. This small, tiny number is e to the power minus 10. Very small number. This is basically to avoid the not a number error, which you're likely to run into if you have values close to 0 or equal to 0 or equal to 1 in certain cases when you're doing a 1 minus blah, 1 minus x. So that situation, you will likely to run a not a number error. To avoid the loss of that situation, smoothing term is added. So we add this expression, very, very small number, added here. And this is added to avoid computing log 0. Log of 0 is not a number. So you add this into before you take the log. So this number is never going to be 0 because of this EPS. So smoothing term. So basically a mathematically inserted expression to avoid not a number loss. It's a very small, tiny number, by the way. And we are calculating our TF square of hidden sigma and hidden mean, adding them up to calculate. Sorry, this is, hold on, let me erase this. I think I must erase that. So erasing. Yeah. This is your latent loss is half of summation of these things. So 1, 2, minus 1, minus TF dot log function of a square of sigmas. That's the loss calculation based on what we just discussed about that different loss that we discussed, which I should point out to you is this guy. What was that name of the two people there, which is not mean square error, but the other function. These guys, this log, the Kullback-Leibler divergence loss. That's what we are really trying to get at, latent loss. Having seen, let's go to the picture again. On the left side here, align it with the pictures like that. what is this thing? Hold on. Close, back. Yes. So we have the loss function. We add our reconstruction loss to the latent loss. So this latent loss gets added to the reconstruction loss, and then we minimize the two together. So this reconstruction loss and latent loss added together, we want to optimize and minimize that loss function. And we also initialize and save, and then we'll run it now in a subsequent step. So with these, I'm going to clear my blue ink and run these things for right now as a variational autoencoder. So I will execute this step. Hello, execute our next step, calculate the loss, and then we will run 50 epochs with a batch size of 150 and let this run for 50 occurrences. Oh man, why that long? But let it run. So it is running, and it'll take some time, but it will show us the idea that we have at hand, which is this idea as to how do we use variational autoencoders by inserting an element of probability in the output of an interim layer. And the implementation of this is what we are looking at. So it is going ahead. I cannot actually execute this next step before the other one finishes, so I have to wait for it. If I reset the graph, it will break the whole thing. Don't want to break it, so I'll just stop right here without executing this step. I'm not executing this one because this training is happening right now. So in the meanwhile, we'll proceed further and let this run. Let's go look at our generated digits, which we have to wait for. The execution cannot happen. But I think at least we can understand what is going to happen when we run it, the generate digits idea. So once we have a model trained, what this model can do is to actually generate few random digits using this approach. And that's what we want to see, to what it can actually produce. So we'll see how it does. Rather, we see the result right now. So here, the plotted result. You can see that the output that this thing produces is actually kind of looks like somebody wrote it by hand. So even here, you see the output in the book on the right side, which is a sample image or set of images generated by a variational autoencoder. And some of these are crazy. Like you can see that it is actually crazy here. Here maybe. I don't know what this thing is. Maybe I do. Excuse me. Maybe it's a 5. I have no idea what this thing is. Maybe it's a 0. This is definitely a made up thing. But yeah, it just trained. It started training only an hour ago. Actually, not even given an hour. So it takes time to produce these things. But when it learns and you run it on the entirety of data set and give it more training time, these digits will look better and better. And you're seeing them already here. Some of them are ugly. Maybe it's a 1. Who knows? Who knows? Somebody might write a 1 like that. Or maybe that's an input. But they're convincingly written by people. But not because it's generated. So that's the underlying idea behind the variational autoencoders. Let's further proceed ahead while this thing runs. And there are more. And this is not going to stop, by the way. This is going to keep on going, these variations. This is a never-ending game until we really accomplish as a humanity really accomplish what we want to accomplish is total artificial intelligence. We are not there yet. Maybe we don't want total artificial intelligence because it becomes creepy. And I'll show you what creepy means. Creepy is Sophia. You may have seen her. Sophia the robot. This is what she looks like. And it creeps me out totally. In fact, the problem with this thing is, the problem with this creepy robot is that it is so real. So real that it talks like a human, it acts like a human, and that's why it makes it creepy. And we don't want to become creepy. We want to have objects that are interesting, that are helping humanity, at the same time not being creepy. So to me, this thing is creepy. It is actually a fantastic accomplishment of, a robot that can sing, understand, speak, talk, move, walk around. It's almost crazy, but creepy. And so that's the robot. You can actually see that you can probably see her videos. I'm calling it her. I shouldn't be doing that. But, Sophia robot video. I shouldn't be saying C. This thing was on Jimmy Fallon just a couple of days ago. And Sophia the robot videos, you can probably see the video. And it creeped me out, totally creeped me out. But it sang a song with Jimmy. And it was totally natural, but that's creepy to me. But okay, enough. Close. And close. And so this autoencoder idea, more variations to that is like this. The reason it is going to blow and grow more and more examples like these will come up is because this field is growing. And that's the idea of unsupervised learning, unsupervised pre-training. It is booming, and you will see more examples coming up. People will do research and come up with. And so here are some variations to that. And they're not described in detail, but almost, I think this is just a list. By the way, there are indexes on these numbers which correspond to the research papers corresponding to these ideas. And this is your contractive autoencoder. What does that do? It focuses on derivatives of the coding with regard to the input are small. What does that mean? It means that, the autoencoder is constrained during training so that the derivatives of the coding with regards to input are small. That translates to, if you have two inputs that are similar, if you write 7 like this and 7 like this, they're conceptually similar. Your coding derivatives, intermediate layers that you will have, the encoded layers, the derivative of that with respect to the inputs are small. That's the underlying math. Effectively, it means you're feeding the same number. So you should have similar coding values, because that's what it translates to, the number 7 as an output, no matter what you feed in here. And that's the underlying idea behind contractive encoder. That's one technique. Stacked convolutional autoencoders. These autoencoders learn to extract visual features by reconstructing images. So trying to visualize and reconstruct. Of course, we have to read the details behind this paper. Another one is generative stochastic network. This has the ability to generate data. It is a generalization of the denoising autoencoder we saw before, with the ability to generate new data based on input data that we have trained. This one is a winner-take-all autoencoder. That means that you have a bunch of activations of neurons. You take only certain neurons, or only certain portion of them, and everybody else is zeroed out. So the winners take all, WTA. They keep all the top so many percent neurons that you have that are active, and everybody else is set to 0. This basically leads to sparse encoders, and that's the definition of WTA as described in this paper 11. There's one more, which is a very, very interesting technique, and that is, I think it deserves a picture. They don't have it here, but I would like to draw it. So I'll draw the picture for this idea, which is, I think, the last idea here. And the picture goes like this. How will I draw this? So let me attempt. The idea is interesting, and that's the reason why I find it interesting. So what we will do is we have a network of layers and layers and layers and layers. And this is the output. Final output matches the input layer. Now what we'll do is we create another network, separate network. Let's call it a fake network. Fake input generator. Let's call it that. And this is a system that generates fake input. And this is your actual input. Actual source, I should say actual source. I'll erase that. So I think I should draw this a little different. So in the input, you can feed it actual data from actual source, or you can feed it with fake data and fake sources. And fake sources can be generated. And so the underlying idea is that you want to have this system detect actual or real versus fake, and tell the true output, the actual output. That's what you want to train the system on, is to be able to detect yes and detect fake and discard it and keep this one. And you will train this network also. You will training this to detect the true actual and keep that as an output and discard these guys. At the same time, you will run a competitive training here. And you will train this system also to generate even more believable fake input. So you train this system to make it increasingly more believable fake as an input to the system, and train this other system to detect those even more increasingly believable fakes and decipher the true real input from the fake input. And so these are two machines competing with each other. On one hand, this guy is trying to detect fake, and on the other hand, this guy is trying to create more believable fakes. And they're fighting with each other. And as a consequence, this relationship of competition will make both the systems robust. This will be able to increasingly learn how to create more believable fake items. And this real input is what real is, or the reality is, and this system will actually detect, even though this faker is actually a super powerful faker and is able to actually create and generate more fake data. That's the reason why the name here is generative adversarial network. And that's the last item in this concept of what's it called? Autoencoders. And so I think on the next session, what I would like to do is go through the last chapter in our book, which is where you have things like Sophia, the creepy one, and other things come into play. So that should be the last chapter, I suspect. I think it is. So yes, it is. So this chapter is about reinforcement learning, which is where you have things like Sophia, things like other robots, and they learn from what's happening to them, and they learn from what is good, what is not good, what is cool, what is not cool, what is right, what is wrong, and they're figuring it out by themselves, and taking corrective action in a feedback loop, and learning from what is happening around them to be able to do the right thing. Let's put it that way. So that's what I will discuss the next time. And I would like to stop recording right now, and I'm open for questions. So I am stopping the recording.